Hello everyone, let us discuss a very interesting topic today. This is about Markov chains. I assume that you already have some basic knowledge of Markov chains. Before we go ahead, please subscribe to the channel. Today we are going to discuss an important question. What is the difference between the stationary state and the limiting state of a Markov chain? We will also discuss under what conditions stationary and limiting states exist. Suppose a Markov chain has 4 states, Q1, Q2, Q3 and Q4. At the start of the time 0, the Markov chain starts in one of these states. At each subsequent time step, it makes a transition from its current state to another state, which may be the same state or one of the other states. So at any particular time, the Markov chain can be in one of these 4 states. These states are mathematically represented as either row vectors or column vectors, depending on the convention being used. We will use the row vector convention. State 1 is represented as a row vector. This is Q1 state. Q2 state is represented as this row vector. Q3 is represented as this row vector, and so on. Q4 is represented as this vector. Although the Markov chain has these 4 states, but mathematically these are not the only possible states of the Markov chain. The Markov chain can also be in a state such as 0.5, 0.25, 0.15 and 0.1, or maybe 0.4, 0.15, 0.15, 0.3. These are also possible states of the Markov chain. This as a whole is a one state, and this is as a whole another state. These are not 4 states. This is one state and this is also one state. You note that the values in a state sum to 1. This also sum to 1. These are called mixed states or probabilistic states. These are pure states. This state means the Markov chain is in state 1. This state means the Markov chain is in state 2. This state means the Markov chain is in state 3, and this state means the Markov chain is in state 4. What does it mean for the Markov chain to be in a mixed state? Say in this state. It means that we do not know with certainty which pure state the Markov chain is currently in. Instead, we only know the probability that the Markov chain is in a particular state. In this case, there is 0.5 probability that the Markov chain is in state Q1, 0.25 probability that the Markov chain is in state Q2, 0.15 probability that the Markov chain is in state Q3, and 0.1 probability that the Markov chain is in state Q4. Notice that these probabilities add up to 1. So this is one state of the Markov chain, but it is probabilistic or mixed state rather than a pure state. Even we can view a row vector as probabilities, where the probability of being in state Q4 is 1. Let us now discuss how a Markov chain transitions from one state to another. The evolution of a Markov chain is governed by its transition matrix. Suppose we have this 3-state Markov chain having states Q1, Q2 and Q3, with the transition probabilities from Q1 to Q2 being 0.4, 0.6, Q2 to Q3 0.1, Q2 to Q1 0.9, Q3 to Q2 0.4 and Q3 to Q3 0.6. Its transition matrix is represented as Q1 to Q1 is 0.6, Q1 to Q2 0.4, Q1 to Q3. There is no edge going from Q1 to Q3, therefore this probability is 0. Q2 to Q1 is 0.9, Q2 to Q2 is 0, and Q2 to Q3 is 0.1. Q3 to Q1 0, Q3 to Q2 0.4, and Q3 to Q3 0.6. Note that the rows of the transition matrix, their sum is equal to 1. Now suppose the current state of the Markov chain is state Q1. What will be the next state if the Markov chain makes a transition? From the transition diagram, we see that next state will be either Q2 or again Q1. There is 0.4 probability that the next state will be Q2 and 0.6 probability that the next state will be Q1. Let us multiply this state with the transition matrix P. We obtain another state, which is 0.6, 0.4 and 0. So this is the next state of the Markov chain. So if the current state is state 1, the next state will be probabilistic state, where the probability of being in state Q1 is 0.6 and probability of being in state Q2 is 0.4. This is how we calculate the next state given the current state. It basically is a matrix multiplication. We multiply state with the transition matrix and we obtain the next state of the Markov chain. Let us now come to our topic. What is a stationary distribution? Suppose a Markov chain has transition matrix P and suppose that its current state is S. This state is such that when the Markov chain makes a transition, so we multiply S with P, the next state is again the same state. Markov chain makes another transition and we again get the same state. This is called the stationary state of the Markov chain. And in most of the cases, this is a mixed state, probabilistic state. But it is possible that the stationary state may be a pure state. Mathematically, a state S is called stationary state of the Markov chain if S multiplied with P is again equal to S. The stationary state of a Markov chain is also called a stationary distribution as well. The reason is that a state vector contains probabilities and these probabilities sum to 1. Therefore, in the literature, the terms state and distribution are often used interchangeably in this context. However, I will use the term state instead of distribution. Whether the state is stationary, limiting or non-stationary, I will simply refer to it as a state. Stationary distribution means the stationary state of the Markov chain and limiting distribution means the limiting state of the Markov chain. Again, a stationary state is a state such that when the Markov chain is in that state, after one transition, it remains in the same state. How many stationary states does a Markov chain have? Unique, just one state, many, or infinite number of stationary states? There is no simple answer. It depends on the underlying structure of the Markov chain. There can be a unique stationary state or infinite number of stationary states. For a finite state Markov chain, at least one stationary state always exists. So there are only two cases for a finite state Markov chain: a unique stationary state or an infinite number of stationary states. If the Markov chain is irreducible, then it has a unique stationary state. Otherwise, if the Markov chain has two or more closed communicating classes, it has an infinite number of stationary states. So the number of stationary states of a Markov chain depends on the number of closed communicating classes. For example, a Markov chain has Q1, Q2, Q3 and Qn. These are the states of the Markov chain. If all of these states communicate with each other, so the Markov chain is irreducible. In this case, the Markov chain will have a unique stationary distribution. Otherwise, if the Markov chain is such that there are two or more closed communicating classes, for example, these states communicate with each other and this is another set of closed communicating classes, then there will be infinite number of stationary states. What is a limiting state? Suppose a Markov chain starts from some state and ultimately settles down to some state S0. Then this state is called the limiting state of the Markov chain. Mathematically, a limiting state S0 is written as S0 equal to limit n approaches to infinity, some state S, transition matrix. For example, we have a two-state Markov chain Q1 and Q2, Q1 to Q2 probability 1 and Q2 to Q1 as probability 1. So if the Markov chain is in state Q1, it definitely goes to state Q2 in the next transition, and from Q2 it transitions to state Q1. Its transition matrix is 0, 1 and 1, 0. Does this Markov chain has a limiting distribution? Is there some state such that if Markov chain transitions infinite number of times and settles down to that state ultimately? There is no such state. For example, if Markov chain starts from state 1, then it goes to state 2, goes to state 1, goes to state 2. It never settles down. It oscillates between state 1 and state 2. So this Markov chain does not have a limiting distribution. From this we can also infer that a Markov chain does not always have a limiting distribution. So how can we determine if a Markov chain has a limiting distribution or not? If a Markov chain is periodic, then it does not have a limiting distribution. Limiting distribution for periodic Markov chain does not exist. Let us summarize about limiting distribution. If a Markov chain irreducible and aperiodic means is not periodic, then the Markov chain has a unique limiting state. Irreducible, aperiodic. It has unique limiting state or limiting distribution. Otherwise, if it is periodic, then limiting distribution does not exist. If it is reducible, means it has multiple communicating classes. For example, these two classes, then if the Markov chain starts from this class, then it will settle down to a state. It will have a limiting state. Suppose it is S0, and if the Markov chain starts from this class, then there will be a limiting state, but that limiting state will be different from that state. For reducible Markov chain, if it has two or more communicating classes, then there will be as many limiting states as the number of communicating classes. But a limiting state will only exist for a communicating class if that class is aperiodic. If there are three classes and one of the class is periodic, then limiting state for that class will not exist. But if the other two classes are aperiodic or non-periodic, then limiting state for those classes will exist. One important fact to keep in mind is that whenever a limiting state exists, it is always equal to the stationary state. Here is summary. If the Markov chain is irreducible, then it has a unique stationary distribution. Otherwise, it has multiple closed communicating classes, infinite number of stationary states. Note that periodicity does not affect the number of stationary states. Even if the Markov chain is periodic, still the stationary state may exist. What about limiting state? Limiting state does depend on the periodicity of the Markov chain. Periodic, if the Markov chain is periodic, limiting distribution or limiting state does not exist. Aperiodic, but depends on irreducible or reducible. If it is irreducible, then it has a unique limiting distribution. If aperiodic but the Markov chain has multiple closed communicating classes, then for each class there will be a limiting distribution if the class is aperiodic. How to calculate a stationary state? Suppose pi represents the stationary state where it is pi 1, pi 2 and pi n, where n is the number of states of the Markov chain. Then solving this system of equations, pi multiplied by transition matrix is equal to pi n, sum of all the i's should be equal to 1. When we solve this system of linear equations, it gives us the stationary state represented as pi. The pi values will give us the stationary state. How about limiting state? Is the stationary state also a limiting state? No, generally it is not. First we have to analyze the Markov chain. If the Markov chain is aperiodic, then the stationary state is also the limiting state. Otherwise, this will be the stationary state and we say that the limiting state does not exist. Thanks for watching. If you find my video useful, please hit the like and the subscribe buttons and share the video with your friends. Thank you.